All right. So we were talking about generation and recombination events. This is what we want to continue this time. Quick recap from last time. We were talking about the concept of optical carrier generation. If you shine light into a semiconductor material, you generate electron hole pairs. Right. We talked about the fact that if you want to generate carriers, the energy of the light that goes into the semiconductor must be larger than the band gap. When that happens, then you get a generation event happening. Okay, an electron goes from the valence band to the conduction band, and now the material becomes more conductive because that electron can move around in the conduction band. At equilibrium, right? Equilibrium, the generation rate and the recombination rates are the same. What we talked about last time is that these two processes are equal to each other at equilibrium, and they are equal to alpha r times ni squared. Okay, alpha r times n0 times p0, electron concentration times the hole concentration. And the intuition behind this was, we said that, if we're thinking about recombination happening, recombination is when an electron bumps into a hole, or in other words, an electron in the lattice finds an incomplete bond, and the two collide, and they annihilate one another. The electron and the hole both disappear. So the intuition is that the more electrons you have, the more holes you have, the higher the probability that they're going to collide. So therefore, the higher the recombination rate. So the fact that recombination rate is proportional to N0 and P0, it should make sense. Now the other intuition is that the recombination rate and the generation rate have to be the same. If they were not the same, that if the generation rate were greater than the recombination rate, then eventually you'll add all the electrons in the valence band will go into the conduction band, and then not only does that physically not make sense, it doesn't happen. The electrons would not all be occupying high energy states when there's a bunch of lower energy states in the valence band available. Okay, that just doesn't happen. So the generation and recombination rates are the same at equilibrium. All right, and since N0 is equal to N0 and P0, N0 times P0 is equal to Ni squared, that's how you get this equation here. Now, the next thing that we started to talk about was this process of generation and recombination events. Okay, this process is happening repeatedly. Electrons are being generated, and then they're recombining. Typically, this process happens over what's called the carrier lifetime. Again, going back to here, talk about the carrier lifetime is the average time a carrier lives before it recombines. So the electron hole pair is generated due to light up here. While the carrier is active, it can move. If there's an electric field, it can drift due to the electric field. If there's a concentration gradient, they can diffuse. But eventually, they will recombine. Okay? This depends on the carrier concentration, as I mentioned. The average time that a carrier lives, in other words, the average time between generation and recombination events is this carrier lifetime. We're going to be talking more about that today. All right, so going back to this map here, this is showing you these generation and recombination events in the energy band diagram. We're going to be starting off class today by doing a problem with this. So here are the steps that happen. First is the formation of an electron hole pair. So this is the valence band, this is the conduction band, this is the band gap, as we've seen many times before. A photon comes and collides with the lattice. Okay, that's what's denoted by the squiggly line here on the left. hv, this is Planck's constant, and this is v is the frequency of the light. So this is the energy of the light, hv, given by Planck's formula. If the energy of the photon is greater than the band gap is this Eg here, then the electron will be elevated from the valence band into the conduction band. Now, in this particular example, there's a relatively high energy light. So the electron is not just going to the conduction band, but it's going well above that. So it gets up to this high of an energy. We'll be doing a quantitative problem on this. So that's step A. That's the generation event. Now, once the electron is elevated to this higher energy state, remember that the electron doesn't remain there. Okay? The electron always starts to find lower energy states to go into. So you can imagine this electron is finding consecutively lower and lower energy states. Remember, this shaded region, the reason we shade it is just to make it easier on ourselves. The shaded region means that there's a whole bunch of energy states at those energy levels. Okay. In the band gap, this is white. That means there's no energy states here. There's a whole bunch of energy states here. So the electron is jumping into energy states that are a little bit less energy than the previous one. That's what's shown by this line here. These are called scattering events. Okay, we can link that to the physical model that we talked about in the last lecture. There's two types of scattering, lattice scattering and impurity scattering. When the electron collides with the lattice, or when it collides with an impurity, it's losing some of its energy. Right? That energy, what is that energy converted to? If something collides with something else in a lattice, it generates heat. That's correct. Right. So these collisions, the electrons are going to progressively lower energy states. This portion, B, is generating heat. Electron loses energy via scattering events and falls to the edge of the conduction band. That's generating heat. Part C. Now the electron has reached the edge of the conduction band. Now if an electron is looking for a lower energy state, the next lowest energy state is all the way down here. All right, that's the key difference between B and C. Here the electron is just going from one energy state to the next one. It just keeps on jumping in small energy increments. But once it gets down here, the next lowest energy state is all the way down here. So when the electron goes from the conduction band, it jumps all the way down to the valence band. That is the recombination event. Okay, the electron in the conduction band disappears, and so does the hole, because this electron is going to come occupy this empty state. Now, this is a large energy transition, much larger than these tiny energy transitions that the electron was going through as it went down as it went to the edge of the conduction band. This energy transition here, part C, this recombination event, it can do one of two things. One is that it could generate heat, just like the other events. The other is what?
Light.
It can emit light. That's right. So if an electron were to lose energy, yes?
So in a B process, they don't emit any lights.
In the B process, generally no. Generally, these small amounts of energy that the electron is losing is generating heat within the lattice.
That's because the energy band, the difference between the top of the semiconductor band and the lower conductor band is like lower than the emitting the light. Is it?
Yes, that's correct. The question was why doesn't part B emit light? The energy transitions, the electron is just going to progressively lower energy levels, and there's very small energy transitions there. So it's not enough energy to generate a photon. Okay. At least not in general cases, not with silicon anyways. This is a large energy transition. This can potentially generate light in certain types of semiconductors. Not all semiconductors emit light. There's a difference between direct bandgap and indirect bandgap semiconductors. We'll talk about that briefly in a little bit, but we're not going to go into too much details of it. Just know this, that the indirect bandgap semiconductors like silicon, they will generate heat. Okay, they do not emit light. But the direct bandgap semiconductors, things like gallium arsenide, gallium nitride, those types of semiconductors do emit light. Okay, those are the materials. The direct bandgap semiconductors are the ones that are used in things like LEDs, lasers, infrared emitters, and so on. So anything that emits light is generally a direct bandgap semiconductor. So this last statement here, the recombination event results in a photon being emitted, the luminescence, that applies generally to direct bandgap semiconductors. Yes, Nasser?
Generate heat and light or just light?
I'm sorry?
The indirect.
Mm-hmm.
Generate heat and light or just light?
The indirect bandgap semiconductors generate heat. The direct bandgap semiconductors can generate light in this step C, when the recombination event happens. And you can imagine that the wavelength of the light that's emitted can be used to calculate the bandgap. Right? I'm answering this question here. So depending on whatever light is being emitted by the material, you're stimulating the material with a certain wavelength of light. And the only requirement here is that the energy of the light has to be greater than Eg. Then what will happen is this recombination event will result in the emission of a photon. And those photons being emitted will be emitted with an energy equivalent to the band gap, Eg. All right, so that'll equate to a certain color of light being given off by the material. All right, so when LEDs are giving off light, these recombination events are happening. The color of the light being given off is dependent on what the band gap of the material is. So they've actually designed materials with certain band gaps to get LEDs to emit certain colors. Okay. The way that you can change the band gap is basically by doing different recipes, like by combining gallium with nitride, but having some aluminum in there, different proportions, different ratios. It takes a long time to develop these processes, but this is how, nowadays we have LEDs spanning the entire wavelength range from 350 nanometers all the way up well into the infrared range. All right, so this is the problem that we're going to do. Same diagram here, except there's some quantitative amounts that we're going to calculate here. So here's a problem. A 0.46 micron sample of gallium arsenide is illuminated with monochromatic light with energy HV is equal to 2 electron volts. Remember, this V here is the frequency of the light. This is Planck's constant. So 2 electron volts. That's shown here. Okay, so the electron absorbs an energy equal to 2 electron volts, so it goes all the way up here. All right, remember that the band gap of gallium arsenide, I think you need that. The band gap of gallium arsenide is 1.43 electron volts right here. Can everyone see this, or is this difficult to see? Okay, let's zoom in here. It doesn't like that. There we go. Is this better? Okay. So you're exciting gallium arsenide. Gallium arsenide has a band gap of 1.43 electron volts. You're exciting that with 2 electron volt light. Okay, the energy of the light is 2 electron volts. Electron will absorb this energy. That's step A. That's the generation event. Then part B, there's scattering events. And part C is the recombination. And in this case, gallium arsenide is a direct band gap semiconductor, so it does emit light. Okay. This process is happening repeatedly. Okay, there's many electrons in the material. These generation, recombination events are happening repeatedly. So the material is generating a stream of photons. You're stimulating the material with a stream of photons, and the material is also generating a stream of photons. So it's emitting light. It's also generating heat because of these scattering events. Right? So this problem, what we're going to do is we're going to calculate the amount of heat generated in the material, and we're going to calculate the amount of light emitted by the material. So we'll go through this problem one step at a time. So the absorption coefficient is 5 times 10 to the 4 inverse centimeters. Power incident on the sample is 10 milliwatts. The first part is to find the total energy absorbed per second. So that's in joules per second. The second part is find the rate of excess thermal energy given up by the electrons due to lattice collisions before recombination. The second part of the problem is talking about this right here. It's talking about the loss of the conversion of this energy to heat. The third part has to do with this portion, okay, the emission of light. Find the number of photons per second given off from recombination events. All right, this is a tricky problem, so I would like to give you just a couple minutes to sort of think through it, and then we're going to go through parts of it as a class. So go ahead, if you grab a sheet of paper and see if you can reason out some of this. Okay, even if you can't figure out the entire problem, that's okay. But see if you can reason out parts of it. So the first part, they'll give you a hint on the first part. In the first part, you have to use the formula that we talked about here, this absorption formula. IT equals IO e to the negative alpha L. So if anyone has figured out the first part of the problem, using that equation, do let me know. All right, has anyone figured out the amount of transmitted light? Okay, let's let me go through this. So I'm going to just redraw the band diagram here. EV. So the distance here, 1.43 electron volts. And this is 2 electron volts. It's losing some energy through scattering events, and then it's falling back down to recombining. Alright, so the first part of the question is asking, find the total energy absorbed per second. It's asking in terms of joules per second. Okay, the absorption coefficient is 5 times 10 to the 4th. Alpha equals 5 times 10 to the 4th centimeters. And the thickness, or the length of the sample, is 0.46 microns, which is equal to 0.46 times 10 to the negative 4 centimeters. 1 micrometer is 10 to the negative 4 centimeters. Okay, Okay, so the first part of the problem is figuring out the energy absorbed. Okay, so we have to go back to this model here that we talked about earlier. We have sample, and we have some amount of light coming in here. The sample has a certain thickness, and that thickness is L. You have some amount of light transmitted. So this is I0, and this is IT. Right. I0 is the incident light. IT is the transmitted light. Now, we talked about this before. Does anyone remember what the units are for the transmitted and the incident light? What are the units for that light? I think I heard it. Yeah? Watts. That's correct. Joules per second. This formula here is talking about watts. So the transmitted light is equal to I0 e to the negative alpha times L. Okay. The units here is given in joules per second. 1 watt is 1 joule per second. So the transmitted light is in watts. I0 is also in watts. All right. By the way, what we're asked here is we're trying to figure out how much energy is being absorbed by the sample. All right. So some amount of light here is going into the sample. Some of it's being transmitted. How do we figure out the absorbed light?
The difference, right?
The difference between the two. Exactly. So this is just think about the conservation of energy. You have some amount of light going into the left. All right. Of the amount that goes into it, some of it's transmitted and some of it's absorbed. So let's just put in IA up here. What happened? This is annoying. All right, I think I need to restart this. Okay. Did we lose color here? No. There's something wrong with this adapter. There we go. All right, so is everyone with me so far? Okay. So there's some amount of light that's is absorbed here, so we'll call that IA. Now, conservation of energy says that I0, the amount of light going into the system, the amount of power going into the system, is equal to the energy absorbed, or the power absorbed, plus the power transmitted. All right? Energy in is equal to energy out. So that's how we're going to figure that out. So we know what the I0 is. We just need to figure out IT, and then from there we can figure out IA. So this is 10 milliwatts. Because we were given that the power incident on the sample is 10 milliwatts. Then we have e to the negative alpha, so 5 times 10 to the 4th, inverse centimeters. And then we the length is 0.4 0.46 times 10 to the negative 4 centimeters. Now you see how these two, the 2 centimeters, cancel out. All right, so this whole exponential becomes unitless. All right, so here we have 10 milliwatts times, if someone can help me out with this calculation here. Should be approximately e to the negative 2 point something. It's negative 5 times 0.46. All right, someone can help me with the math there. We will get the transmitted light. If I remember right, yeah? Oh, 0.1, okay, thanks a lot. 0.1 times 10 milliwatts. If any of this is confusing, please do stop me. Okay. All right, so the transmitted light is 1 milliwatt. So the first part of this problem, we have figured out that this is 1 milliwatt transmitted light. The absorbed light is 10 milliwatts here, 1 milliwatt here. So the absorbed light is equal to 9 milliwatts. All right. And the incident light is 10 milliwatts. That's the first part of the problem, figuring out the energy absorbed. So the answer to this question, and when I give you questions on quizzes and exams, I want you to box the answer and make sure you have the correct units. So the question is asking, find the total energy absorbed per second. That's IA. So the IA is equal to 9 milliwatts. So 9 milliwatts is 9 times 10 to the negative 3 watts, and 1 watt is 1 joule per second. So 9 times 10 to the negative 3 joules per second. That's the answer to the first part. Any questions about the first part of the problem?
Would 9 milliwatts be acceptable on the exam, or do you want it in scientific notation?
Yeah, 9 milliwatts is fine. Mm-hmm. All right, the next part of the problem is asking, find the rate of excess thermal energy given up by electrons due to lattice collisions before recombination. So this is just a different way of saying that what's the amount of thermal energy being generated in the material. The rate of heat generation in the material is what the question is asking. All right, well, specifically what it's saying, the rate of excess thermal energy given up by electrons. So these scattering events is causing the electrons to give up excess thermal energy. So it's generating heat in the material. This is also in joules per second. Now this particular problem, can anyone think of how we might solve this problem? And I'll give you a hint. The calculation here is actually very, very simple. And it has to do with the energy band diagram. So let's zoom in on the energy band diagram here. It has to do with this number, and it has to do with this number. So I want you to analyze the energy band diagram and think about an electron being, electron absorbing some energy. Some of the energy is being given off as heat. Some of it's being given off as light. So let me ask a more pointed question. What percentage of the electron's energy is being given off as heat? Let's figure that out. So just looking at this diagram, what percentage of the electron's energy is being given off as heat?
Like around a quarter.
I'm sorry?
Around a quarter? Well, I'm just saying if you took the difference, then
Divide and subtract from 1.
Well, yes?
Divide and subtract from 1 and multiply by 100 to get the percentage.
Yes. How do we figure out the amount of how much energy is for each electron? How much thermal energy is being generated in the material?
1.4 over 2, right?
Well, 1.43 volts is how much is being given off as light. So think of this in terms of energy. Each electron absorbs 2 electron volts of energy. One photon goes in there, the electron absorbs that photon, it gains 2 electron volts of energy. And then how much of the energy is being lost, converted to heat? I think I heard it. 0.57. That's correct. It's 2 electron volts minus 1.43, right? So this distance here, this is 2 minus 1.43. So this is equal to 0.57 electron volts. Very good. So an electron absorbs 2 electron volts of energy. 0.57 electron volts of that energy is converted to heat. 1.43 electron volts of that energy is converted to light. All right. So from here we can just do this simple calculation here. So this question is asking how much thermal energy is generated in the material. And it's asking in terms of joules per second. The way that we'll figure this out is we can make this argument that says each electron, again, same thing again, 2 electron volts absorbed, 0.57 electron volts is lost as heat. So we can say the percentage converted to heat is equal to 0.57 electron volts divided by 2 electron volts. Okay, and what does this come out to? 0.57 divided by 2. Okay. 28%. 29%. All right. So about almost 30% is being converted to thermal energy. So if we're trying to find that out in joules per second, we take the absorbed energy, absorbed equals IA. I'm sorry. Let's say that the rate of thermal energy generation is equal to the absorbed energy multiplied by this 29%. Okay, and the absorbed energy was 9 milliwatts. About a third of that will be something like 2.5 to 3 milliwatts, I think. 9 times, and maybe about 2.6 milliwatts. So the rate of thermal energy generated in the material is 2.6 milliwatts. Going back to this diagram, okay, I want you to understand conceptually what's happening here. Again, we have the incident light here, we have the transmitted light, we have this absorbed light. Now from the absorbed light, 9 milliwatts was absorbed. If we subdivide this again, we can say that 2.6 milliwatts is converted to heat. Okay. And of the 9 milliwatts, the remainder is converted to light. Right? Because each electron loses some of its energy to heat and some of its energy to light. So out of 9 milliwatts, if 2.6 milliwatts is being converted to heat, the remainder is being converted to light. So this will be 6.4 milliwatts is being converted to light. All right, so the answer to part B is 2.6 milliwatts. So let's box that there. And part C has to do with the light generation. Now, part C is actually asking us to go one step further than that. Find the number of photons per second given off from recombination events. So it's asking in terms of the number of photons per second. If it was just asking how much light energy is being given off by the material, what is the optical power of the light emitted by the material, then that would be a very easy calculation. So let's just write this down. The number of photons per second emitted. We'll do the easy problem first. Let's first find the power emitted. The power emitted equals the absorbed energy times 100% minus 30%. Right? So 71% here. Does everyone see how I got 71%? Yes? Because some of that energy is being 29% is being converted to heat, the remainder is converted to light. All right, so this comes out to, what do we find here? 6.4 milliwatts. So this is the optical power emitted by the material. Remember last class I said that optical power, you can think about power in terms of the number of photons per second being given off by the material. The energy of the light is determined by the wavelength. The power of the light is determined by how many photons being given off. If we look at the like a red LED, for example, the energy of the light is just determined by the color of the light. Regardless of how brightly we turn on that red LED, we cannot change the energy. By making the LED brighter, by running more current through it, what we're doing is we're changing the power. We're changing the number of photons per second given off by the material. So right here we figured out the optical power emitted by the material, that's 6.4 milliwatts. It's asking us to find that in terms of photons per second. So we just need to do a simple calculation here. Simple unit conversion, 6.4 milliwatts. All right, if you remember how to do these unit conversions, first we want to convert to joules per second. 1 milliwatt is equal to 10 to the negative 3 watts. Okay, I'm putting in extra steps here, so just bear with me here. 1 watt is equal to 1 joule per second. All right, now we need to convert this into photons. So first we need to convert this joules into electron volts. 1 joule, 1.6 times 10 to the negative 19 joules is equal to 1 electron volt. And now this is the part of the problem that has to do with the energy band diagram. We want to see how many, the units that we want here is the number of photons per second. All right, so we need to convert joules per second into photons per second. So what we're doing here is we're going through this intermediate step, converting the joules into electron volts first. This part does the conversion from joules to electron volts. And then we have to say that 1 photon emitted has how many electron volts of energy? Let's go back to the energy band diagram. Every photon emitted is giving off 1.43 electron volts of energy. All right, so now if we do the unit cancellation here, the milliwatts cancel, the watts cancel, the joules cancel, the electron volts cancel, and we're left with photons emitted per second. So if someone can help me out with the math here. So 6.4 times 10 to the negative 3 divided by 1.6 times 10 to the negative 19 divided by 1.43. .79 times 10 to the 16th? Okay, thank you. 2.79 times 10 to the 16th photons per second. That's a lot of photons. 2.79 times 10 to the 16th. This is the final answer here. All right, so just to recap here, to figure out the number of photons per second emitted, we first had to figure out the amount of optical power. We figured out that there's 6.4 milliwatts of optical power. Now, 6.4 milliwatts of optical power means that the logic here is that every electron, every photon that's emitted has 1.43 electron volts of energy. And that can be converted to joules. So there's a certain number of joules of energy that each photon has that's being given off. And so if there's 6.4 milliwatts of power, if there's a certain number of joules per second in terms of the optical power, then from there you can figure out the number of photons emitted by the material. And the way that you can do that is by the simple unit conversion, just this last step at the end here, you have to say that one photon emitted has 1.43 electron volts of energy. Yes?
Can you explain the logic of the 71%?
Yes. The 71%. Oh, this part here. So out of the energy that's absorbed in the material, we have 9 milliwatts that was absorbed. Some of the absorbed energy is converted to heat. Some of the absorbed energy is converted to light. And the way that we understand that is by looking at the energy band diagram. All right. This energy band diagram is showing what happens when an electron is absorbed. So the energy band diagram has nothing to do with I0. It has nothing to do with IT. It's really talking about what happens with the absorbed light. So the electron absorbs 2 electron volts of energy. It loses some percentage of that energy. 29% of that energy is lost as heat during this portion of the process. And then the remainder, 71%, is converted to light. That's this part of the process. So that's where the 2 percentages came from. Did that answer your question, or was there something? Okay. Okay. If you have any other questions, come after class. All right. So we were just doing calculations based on that idea of the energy band diagram. So there's a lot of different concepts here. If you are not sure about it, you can go over this problem again. I should have it posted later today. Again, this will not be on Thursday's test, but it will be on a quiz that we'll have the following week. Okay. I'd say this is one of the more difficult problems that we do in this chapter, but you'll see that Module 4 actually has some of the more challenging problems for the course of the entire semester. I would say this is one of the most difficult modules, okay, because later we're going to be talking about diffusion, recombination, and a bunch of things together. The math for this problem is actually not that difficult, but there's a lot of concepts to think through. Any other questions? All right. So let's continue on a little bit further, and then we'll take a break. So there's a few different types of luminescence. Since we were talking about luminescence here, I just want to take a bit of an aside and talk about the different types of luminescence that different materials can have. One is photoluminescence. This was an example that we just looked at. We excited the semiconductor material with light. Okay, in the problem that we did, the light had 2 electron volts of energy, and then the luminescence was coming out at how much energy was the luminescence that's coming out? In the problem that we just did,
1.43.
1.43 electron volts, right? Determined by the band gap of the material. So photoluminescence means that light is used to excite the carriers, and light is being emitted by the material. Besides the semiconductor example that we saw here, other examples are fluorescent tubes. The excitation is coming from electrical discharges in the tube, which generates a spark, and that spark causes the phosphor to absorb that light, and the phosphor gives off light at a lower energy. Right. Similarly, what's happening here is that the electron is absorbing high energy light, and it's giving off, the material is giving off lower energy light. Electroluminescence, this is where an electrical current is used to excite the carriers. That's what happens in LEDs. So an LED is a light-emitting diode. Turns out when you run an electrical current through there, that generates recombination, and that's what causes the LED to emit light. This is a very important phenomenon because this is the basis for solid-state lighting. And then the final type of luminescence is cathode luminescence. This is the type of luminescence generated by when you bombard phosphors with electrons. So the CRT displays, cathode ray tubes, the old style televisions, the big heavy bulky ones, those were based on CRT technology. That's where, I'll just draw this real quick. So a CRT looks something like this. They had an electron gun. This was the front of your TV, so this was the glass. There's an electron gun at the back of the TV, and the electrons were basically accelerated towards the glass of your TV. And when the electrons hit the glass was coated with a phosphor, and that phosphor gives off a brief pulse of light. So the phosphor is what gives off the photons. And the electrons were sort of scanned, raster scanned back and forth to generate an image on the TV. Unfortunately, this type of technology was quite bulky and heavy, hard to scale it up to large TVs. So now we have our LCD displays, which work in a fundamentally different way. The LED displays actually have today's TVs work something like this, where there's a grid. This is looking at it from the side view, and there's a light source in the back. So we're sitting here. There's a light source in the back, and that light source is going through here. And each one of these pixels on the screen, so in an HD display, I think you have 1 million pixels on the screen, something like that. You can do the math, 1920 by 1080. That's the number of pixels you have on the screen. So these pixels can either become dark, they can either become opaque or transparent, depending on the voltage that you put on the pixel. They can switch states. So you can imagine that if if you're looking at this from the front view, if you have a bunch of pixels on the screen, some pixels are light, some pixels are dark, you have a display. You can make a display this way. All right, so this type of approach, this is what's called the LCD panel, liquid crystal display. These pixels are actually made of liquid crystals. Liquid crystals become opaque when you apply voltage to them. Or, don't remember. The transparency of the liquid crystal depends on what the voltage is, what type of voltage is placed on them. All right. So this has less to do with luminescence, more to do with liquid crystal technology. The old type of CRT displays had to do with more with like this phosphor coatings that gave off light when the electrons hit it. So that's cathode luminescence, which we're not really talking too much about this chapter. So these concepts, just know them from a conceptual standpoint. We're not going to be talking much more about them here. Most of the emphasis here is on photoluminescence. So examples of luminescence, light-emitting diodes. Again, this is electroluminescence. These are semiconductors, direct bandgap semiconductors such as gallium arsenide, indium phosphide, other materials. The key here is direct bandgap. You have to have a direct bandgap semiconductor if you want to make an LED. Again, LED is a light-emitting diode. This is not going to make sense at this point. This is showing an energy band diagram of a diode. We'll get to that in the next module. But what I want to draw your attention to is here. The recombination of electrons recombining with holes in the valence band, these recombination events is what causes light to be emitted. So the amount of energy lost during this recombination event is basically the band gap of the material. So by choosing different materials with different band gaps, you can get different color LEDs like you see here. Okay, like I said, we have LEDs that are commercially available from the 350 nanometer range, not just in the 650 nanometer range. It goes well beyond that. It goes into the infrared range. Okay, so engineers have developed a wide range of materials with different band gaps so that we can have LEDs of different colors. As of 2009, you could get LEDs 250 nanometers all the way to 1100. And as we know, like this was back in 2012, but by now, like solid-state lighting is pretty much the standard for the new standard for lighting in terms of energy-efficient lighting. Another example of luminescence is quantum dots. Quantum dots are photoluminescent materials. They're particles made from a semiconductor called cadmium selenide. Now, there's something very different about quantum dots that we're not going to study in this class, but it's something interesting that you can know. In LEDs, the color of the wavelength, the color of the light being given off is determined by the band gap of the material. In quantum dots, this is why they were so interesting. In quantum dots, the wavelength of the emission was determined by the size of the particle, not the material itself. So by using cadmium selenide of various sizes, same material but different size particles, you could get different colors of light being emitted. The reasons for that we're not going to go to in this class, and I don't expect you to know that for the exams. But what happens is that if you have really, really tiny particles that are on the order of the wavelength of light, the way that you solve the Schrodinger equation, the boundary conditions change, and you have a different set of energy states available for electrons. So the material behaves differently than traditional semiconductor materials where we have a large lattice. Quantum dots, like the size of quantum dots are like on the order of nanometers. So it's along the same size as the wavelength of light. So quantum dots became commercially available in 2005. They're widely used in biological research for fluorescent tagging, although there's some concerns that they are toxic to cells. Nonetheless, they are used in various types of research. You can see that these nanoparticles, small particles, have different colors depending on what their size is. Okay, so let's stop there. We'll get into recombination after the break if we have time. Let's take a 2 or 3 minute stretch break, and then we'll do the presentations. Michael, do you want to go first? Okay. Like I said, what I can tell you about the test is what I mentioned before. There's about like four, maybe 5 questions, 1 extra credit. About half of the questions will be calculations, half of them will be short answer. Another thing I didn't mention before is that I sometimes do the questions like of some easy questions and then some harder questions. Like the 4 or 5 questions they'll be graded, not they'll have different difficulty levels. The reason I do this is because there's I want the easy problems. I want all students to be able to get the easy problems. Okay, the more difficult questions, I want the students who really know this stuff really well. I want them to be challenged by the more difficult problems. That being said, some of you might think all the problems are easy, and that's great. Some of you might think all the problems are difficult, in which case you should come talk to me after the exam, and I'll try to help you through and help you understand the concepts.
Will
Okay.
it be an even point distribution between the problems, or will they be graded based on the difficulty?
The question is, will there be an even point distribution among the problems? I typically assign points according to how long the problem should take. So if you see one of the problems is like 35 points, the other one is like 15 points, chances are the 15-point question will be quicker. I would say do the short answer questions first. That would be my advice on the test, because those types of questions, you either know it or you don't. So at least a first pass, you may just go through and answer the short answer questions quickly. If there are ones that you can't get that you want to come back to later, do that. The calculation type questions, honestly, on the first test, you can see from your quizzes and the homeworks that the number of calculations that you have to do here, it's not that bad. It's not that time consuming. The calculations we'll be doing in the diode chapter, the MOSFET chapter may be more involved. Those will take more time. So I would say for this first test, know the concepts really well, know the homework questions really well. Make sure that you can do the homework questions without the solutions. While you're doing the homework questions, look over the concepts that relate to those homework questions. Don't just do enough to answer the question. Make sure you understand all those concepts, because that's where the short answer questions will come in, conceptual understanding. Yep.
Will you use scratch paper? Like, I don't know how much room is going to be on the test for.
Oh, yeah.
writing and
I'll bring some extra scratch
okay.
paper for everyone to use. Yeah, good point. Yeah, usually I give you room on the test to do it, but if you need some extra scratch paper besides that, then no problem. So the tests are about 20% of your grade, so it is a substantial portion of your grade. It's obviously worth a lot more than the quizzes. Each quiz is probably worth 2% of your grade, something like this. So the tests are really what is really what it counts. Any other questions then? Okay. If you have any questions between now and Thursday, I will have office hours Thursday before the test, but also if anyone would like to have any questions tomorrow, let me know what time you'd like to come in, and you can come to my office. We can discuss it then. I should be here tomorrow in the afternoon.
Would there be any benefit to looking through the book at all?
Would there be any benefit to what?
Looking through the book?
Looking through the book?
Other than doing the homework with
There is some benefit to doing some of the example problems. If you're done with all the example problems in the homework and you want to do some more examples in the book problems are harder, but if you can do those, the exam will be cake for you. Okay. All right. So we have then 15 minutes left. Let's go over some more material. So we talked about luminescence. Now let's talk about a little bit more about recombination. There's 2 types of recombination. There's direct recombination and indirect recombination. So direct recombination occurs in direct band gap semiconductors. Recombination is directly from the conduction band to the valence band. So this is what we just saw earlier. This occurs in direct band gap semiconductors like gallium arsenide, and the energy loss from recombination is often converted to a photon. So this part C here. Another thing about direct recombination is that it's fast. Typically, the carrier lifetime between generation and recombination events is less than 10 nanoseconds. Compare this to indirect recombination. All right, in indirect recombination, you have an intermediate energy state within the band gap. Okay, And that is what's responsible for the recombination. So what happens is that the trap will capture a hole from the valence band. So this is part A here. A hole will, or rather an electron will drop down from the trap level into the valence band. And then an electron will drop from the conduction band into the trap level. So effectively, this is the same thing as an electron, or it's equivalent in some sense to an electron going all the way down to the valence band, except it's happening in 2 steps. For that reason, this indirect recombination process is typically slower than the direct recombination. And the other important point here is that the energy loss from recombination is converted to heat. Generally, light is not given off in this case. So one thing you may be asking is, well, how do we get these trap levels in here? Because before we said one of the features of a semiconductor is that you have this band gap, a certain a range where there's no energy states. So how do you think we can get a trap level? We have hinted at this before in chapter 3. So let's test our knowledge on that. How do you get an energy level within the band gap? What's one way to do that? Doping, exactly. If you recall that if we dope the semiconductor, if we dope silicon with a column 5 element, there's an energy state that energy levels that appear near the conduction band. And if we dope with a column 3 element, then there's energy states that appear near the valence band. Okay, that was critical to how you develop different carrier concentrations in doped material. This particular example is showing a trap level that's sort of closer to the middle in between EC and EV. But again, the main point here is that it occurs in 2 steps. An electron drops down from the trap level into the valence band, or in other words, a hole goes up from here from the valence band into the trap level, and then an electron comes down from the conduction band into the trap level. So it occurs in indirect semiconductors like silicon. This slide shows the different trap levels that you can get by doping the material with different impurities. So like we said, if we look up here, arsenide, that's a column 5 element. And remember, when you dope the material with column 5, you generate an energy state that's very close to the conduction band. All right. Phosphorus is also a column 5 element. Arsenic. Okay, these have energy states very close to the conduction band. Some common column 3 elements, boron, for example, gallium and aluminum. Column 3 elements, they generate trap levels near the valence band. There are other materials that will generate trap states closer to EI. For example, gold. Gold generates trap states very close to EI. Copper, zinc, magnesium. One of the practical implications of this technology is that sometimes you want to have a pure semiconductor. You don't want to have these intermediate states because they affect a lot of carrier processes. You can see here that it affects recombination. So what this chart is showing is that if the silicon lattice, if it has impurities in it, then you'll end up having these trap levels, and they will affect the behavior of the semiconductor material. Why do you think that in a clean room you have people wearing those bunny suits? There's HEPA filters to prevent any type of contamination. The water used in a clean room, the water, you'll see when you go to the microfabrication facility here in our department, you'll see that the water that's used here, it's deionized water. Deionized means all the ions have been removed. Very, very ultra pure water. If you have ions in there, if you were to use the tap water, for example, tap water, as you know, has a lot of ions in it. Well, if you happen to have copper ions in your water, guess what happens to your silicon? Copper creates intermediate energy states within the silicon. If any of those copper ions gets into the silicon wafer that you're washing, then you end up having intermediate energy states. Your material will not behave as a typical semiconductor material will. Copper, magnesium, even small amounts of gold, zinc, these types of ions are common in city water. All right, but copper, I would say, is more common. You have copper pipes. Sometimes the copper ions from the pipes leach out into the water. So you have to have ultra pure water when you're dealing with semiconductor processes, or you will inadvertently put trap levels into your silicon, and you'll end up with having these types of processes happen. Now, sometimes you intentionally want to put those impurities in there, as was the case with doping, column 5 doping, column 3 doping. In some cases, you even want to get energy states near the intrinsic level. Sometimes you'll intentionally dope, and in other cases, when you don't want to dope, you have to make sure that you use ultra-pure manufacturing processes so you don't do this type of, create these trap levels inadvertently. So moving on to carrier lifetime now. All right, carrier lifetime, as I mentioned, it's the average time a carrier exists before recombining. It's the average time between the generation and the recombination. So this slide is showing a formula for the carrier lifetime. So the idea here is that suppose at time 0, we have a silicon wafer, or we have some type of semiconductor material, and at time equals 0, we apply a short flash of light to it. And the question we're asking is, how long will it take for those electron-hole pairs to recombine? That flash of light has created a bunch of carriers in the material, right? So how long will it take for those carriers to recombine once we turn the light off? That's what the carrier lifetime is, or that's how we can define it in experimental terms. The way that we can mathematically define this, we define sigma n of t as the number of excess carriers at time t. Let me jump ahead here for a second, just show you this picture here so you get an idea of what we're talking about. You have a semiconductor material and you just illuminate it with light. When you illuminate it with light, you're going to generate these carriers, right? You're going to generate electron-hole pairs. Blue are the electrons, white are the holes, okay, just schematically. When you turn the light off, those carriers are going to then recombine. So the electrons and holes will basically disappear. Those excess electrons and holes that you've created will disappear. So going back to this, so sigma n is the number of excess carriers at time t. Now what do we mean by excess carriers? You have a certain number of carriers in the material already. So again, just so you have a picture here, a semiconductor material, we have silicon, right? Silicon already has electrons and holes in it, right? At room temperature, silicon has electrons as well as holes. But when you shine light on the material, you're creating excess electrons and holes. That's what I'm showing here in this picture. That's what we call excess carriers. That's why this module is called excess carriers. We can generate excess carriers by applying light to the material. In fact, this is the basis for solar cells. So sigma n of t is the number of excess carriers in the material at time t. The rate of change of excess carriers, d sigma n of t dt, is equal to the generation rate minus the recombination rate. Now, when we do this type of experiment, we are applying light at time equals 0 and we're turning the light off. This temporarily changes the electron and hole concentration. It's a non-equilibrium situation, so the generation rate and the recombination rate are not necessarily equal to each other. So that's why we have this equation here. And the generation rate minus the recombination rate. At equilibrium, these two would be equal. D sigma n dt would be basically 0. But in the non-equilibrium situation, we have this differential equation that's saying that the rate of change of the excess carriers is equal to the generation minus the recombination rate. Okay, the generation rate is alpha r times ni squared, the same as before. The recombination rate is equal to alpha r, if we back up here. You know, this equation was showing alpha r times n0 times p0, so it's the recombination rate constant multiplied by n0 multiplied by p0. So what we have here through the recombination rate, it's not alpha r times n0 times p0, it's alpha r plus n0 multiplied by these two factors. Okay? What's happening here is that the recombination rate is increasing because we have excess electrons, we have excess holes. Okay, we'll talk more about this in the next class, but you know, when you put light on the material, you're generating extra electrons, you're generating extra holes, and so you're basically increasing the concentration of electrons, you're increasing the concentration of holes. So therefore, the recombination rate is going to go up. The intuition there, remember, the more electrons and holes you have, the higher the probability that they're going to collide with one another. All right, so this N0 and P0 now becomes N0 plus the excess, P0 plus the excess here. So this sets up a differential equation here. If you solve this differential equation, assuming a few things here. Number one, you have a doped semiconductor that P0 is much greater than N0, or N0 is much greater than P0. In other words, you have an N-type or a P-type semiconductor. That's the first assumption. And the second assumption is that you have low-level injection. We'll talk more about that in next class. Low-level injection means the amount of excess carriers is much less than the number of total carriers that you have in the material. So in other words, sigma n and sigma p are much smaller than N0 and P0. We'll talk more about that next class. We'll make sure that we define it, because there's a lot of notation in this chapter. I think it's helpful to have, we'll have a list of what all the notations mean. All right, and this is the equation for carrier lifetime. So this equation can help you solve one of the problems in your homework. So what is this equation? Sigma n of t is equal to delta n e to the negative t over tau. And this is the tau n is the carrier lifetime, 1 divided by alpha r times N0 plus P0. Okay, this is the solution to this differential equation. Now, in the last few minutes that we have, I just want to go over what this equation means. Now, many of you have seen an inverse exponential function. Let's try this here. What does an inverse exponential function look like? So this is t. So we have sigma n of t equals delta n e to the negative t divided by tau. What does this equation look like if we graph it? So this is sigma n, and then on the x-axis we have t. What does that look like? Yes, inverse exponential, right? Like this. Let's relate this back to the problem that we were talking about, because I want you to, it's important for you to see the equation and what it means. So what we did is we had a semiconductor material. We shine light on that material, okay, and then we turn the light off. So when we shine light on the material, we created electrons and holes. When we turn the light off, those electrons and holes recombine, so the excess carrier concentration goes to 0. This sigma n here is the excess electron concentration, excess hole concentration. Okay, we define sigma n is the excess electron concentration. So this is given in 1 per centimeter cubed. Sigma p, which is equal to sigma n, is the excess hole concentration. Why is sigma p equal to sigma n?
Each electron has a hole.
Yeah, they're created in pairs, right? So on the y-axis here, I could say sigma n. I could also say sigma p. But let's just keep sigma n for now. This equation is telling us that when we turn the light off, if we turn the light off at t equals 0, the excess electron concentration at t equals 0 will be equal to some value delta n. We'll call that delta n. And that's what this is right here, this part of the equation. Okay, as time goes on, the excess carrier concentration is going to decay exponentially. That's what this equation is telling you. It decays exponentially, and that is according to this time constant. This is the carrier lifetime. All right, I'm going to draw 2 plots here. Just draw this in a different, shoot. All right, I'll draw one in blue, and I will draw one in green. Which one of these has a larger carrier lifetime?
Green.
The green one has a longer carrier lifetime, right. It takes a longer time for these carriers to decay, to die out. It takes a longer time for it to recombine. So this is an example of large tau, and this is an example of small tau. This is so you understand the importance of this this tau in the denominator here. This is the rate constant. This is telling you how quickly that exponential function decays away. All right. A small tau will mean you're going to get a rapid decay. A large tau means a more gradual decay. So the longer carrier lifetime, to relate it back to the physical thing, the longer carrier lifetime means the electrons and holes exist for a longer period of time before they die out, on average. So again, this is a graph of time versus the excess electron or hole concentration. So the carrier lifetime here is shown is here. So this is large tau. This is an example of small tau. And the way that you calculate the carrier lifetime is 1 divided by alpha r times n0 plus p0. For this class, most of the time I will give you the carrier lifetime. You won't need to calculate it. What you will need to do in your homework problem is that you'll have a given problem saying, this is the electron concentration, hole concentration. I'm sorry, this is the excess electron and hole concentration at time equals 0. Find out what the excess electron and hole concentration is at time equals 2 nanoseconds. Or one of the homework problems is how long will it take for 99% of the carriers to recombine? Right? Just using this exponential equation, you can figure that out. Okay, so we will stop there for today. Again, the test is Thursday. We'll start at 3:30, maybe 3:35. So please make sure you're here on time. Any questions you may have about the test, you can send me by email. I will be here this afternoon, or I will be here Wednesday afternoon if you want to come in and talk about anything.
So, I got a question about the homework number 1.
Sure. Just a second.